Hi everybody. Well, all right, we are now at part 4 and we're going to continue our circuit analysis here, taking our measurements. And where we left off was we looked at the front end, the differential pair, input pair. And we talked a little bit, took some measurements of the voltages and kind of talked about how those voltages came to be. And now we're going to look at our voltage amplification, or our VAS stage, which also is going to control our drivers and our outputs. And it's also, we're going to talk a little bit about this bias circuit. And then at the very end of this video, we're going to just have a quick listen to it, just to find out what it sounds like in its stock form. Let's get started. Alright, I have this powered up now, and I have it about as close to 12 volts where we were from the last video part as we could get it. And we're going to start taking some measurements of Q6. And I think, in addition, that would be also Q5, so it just depends which channel. So looking at Q6, or Q5, whichever you want to call it, of course, this first one is on the other side of R23, which is a 22 ohm resistor. This is kind of like a poor man's voltage regulator. This will drop the voltage a tiny little bit, but it will also help make this a little more stable. Now, remember, on higher end units, they will actually have a regulated power supply that will come in and power all of this. But in this one, they're using VCC. Now, I'm using a highly regulated bench power supply to drive this whole thing. So we're not going to have any problem here. But normally, if you had a transformer, especially the little tiny transformers that they usually pair up with these, as the transformer starts to have some sag, some voltage sag, it really won't do anything to this section here, because you're not going to get anywhere near dropping the voltage below where it needs to be to drive this. But what you will see is that little bit of voltage fluctuation, it will introduce itself into here. And again, that would be a really advantageous thing then to have a constant current source in this end, because that would kind of help with that a little bit. Although you still do have this 33K for the for your current source. Again, all this stuff is theory, and we can talk about this all day long, and you can model it on a computer and do whatever you want, but really, until you listen to it with your ears, that's all fun to talk about, but a lot of things we find out a lot more just by experience. So, let's take some measurements of Q5, which is going to be our VAS stage, which is also the same as Q6, which that's the easiest for me to reach. So again, we have emitter, base, and collector going this way. So let's see if we can get everything in shot. There we go. So looking at the emitter of Q6, and that is right here, or Q6, yeah. I should see, oh, wait a second. This is the emitter. I'm looking, this transistor is backwards. It's facing that way. So there's our 12 volts, and that's what it should be. Going to the base, let's look at the base, is 11.35. So let me write that down. 11.358. And then, of course, the collector, which is going down to your driver transistors, is 0.7176. So right here we have 0.7176, or 717.6 millivolts. So Just to confuse you all, sometimes I write millivolts and sometimes I write the decimal. Why do I do that? Well, because it's Tony. Nothing but the best on this channel. All right. So this is going to set up the bias for your output section. And again, from this part back, we're amplifying the voltage. We want the amplitude of the signal to go up. But we're not really driving any kind of a load. The load that these are connected to are all higher impedance, and they don't require a lot of current. So what we want to do is we want to eliminate, that would be inefficient and cause heat and everything else. We want to keep this side cool. And so this is all low current stuff. But we're amplifying the voltage, or amplifying the amplitude of the signal. When we get to these sections here, our voltage level, by the time we get here, is where we need it to be. But now what we want is, we want to be able to drive a low impedance load to this voltage level. And in order to do that, you have to be able to handle the higher amount of current that you're going to need. So this isn't really voltage gain here. Some circuits will do that. They'll have a little bit of voltage gain, but for the most part, they're designed to not have voltage gain, but to actually have current gain, so you can actually pass the heavier current. So if we look here, we want to turn these transistors on. We want to bring them right into conducting just a little bit. And that's what this is doing right now when it's sitting idle. So if I measure here and I look at the voltage, and then I measure here at the voltage, what do you think we're going to get? Let's look all the way down. We'll go to D4 and then to D2, or at least on this side it will be, yeah, D4 and D2, or D3 and D1, whatever the case may be. So here's D4 and D2 right over here. So if I go here, this is going to be that 717 or whatever it was, or 7178. And then if I go down here, and you can see I'm down to 570 millivolts at the cathode of that diode. So yeah, 56.68 millivolts. So 56.68 millivolts. Then if I go across to the other diode, I have negative 603 millivolts. So there's actually a negative voltage there. See that? Minus 603.2. Now, of course, the reason that's negative is because it's being fed from this negative supply here. And there's another 22 ohm resistor. There's your negative VCC coming in. Remember, this is a PNP transistor, so it needs a negative voltage on it. Whereas this is a NPN, it needs a positive. It needs a more positive voltage, as we learned from this last lesson over here, right? So if we look at the actual difference between here, if I just go straight across there and I go from here to here, and I probably should turn this down, I have 1.3 volts. And that's going to be those two diode drops there. I'm going to try something here. Give me a second. All right. So we have 1.32 volts forward voltage drop. And that's essentially the difference between these two diodes. And it's supposed to hold that there. And by having that voltage between these, it's going to ensure that these are both going to be just slightly turned on. That's your bias circuit. Now, I don't know, I haven't tried this yet. Let me move this stuff around. But if I put my finger on here, let's see what happens to this voltage. I'm just holding my thumb on the two diodes. See how they're moving as it heats up? The heat from my finger, which isn't a whole lot, is actually heating those diodes up. Now if I take my finger off, it'll start going back up as it cools. And if I fan it with my hand a little bit, it'll go up faster. See that? And that's called bias creep. Now, if I even go more extreme, and I just blow some hot air on it, there we go. See what happens? It moves a lot. That's your bias voltage changing. And that's called bias creep. And this is what you don't want to have happen. In other words, you don't want those to be able to change independently of your driver transistors and your output transistors. You want them all to track the same way. In theory, what would happen is if these were connected to these transistors, they were all on the same heatsink, let's say, or they were all kind of glued together, what would theoretically happen is as this heats up, this junction here would do the same thing that this junction on this diode is doing. And the whole idea is one would offset the other. That's what we're actually trying to do with, when we're using thermal management in a bias circuit. So normally you would see something in here that would have a same characteristic as this, and it would move the voltage in an equal and opposite direction that this is moving here to offset it. And that minimizes, it may not totally eliminate, but it will minimize that bias creep. Now, if bias creep gets too bad, what will happen is if the bias goes too low, the transistors won't be turned on enough, it won't be conducting enough, and you could possibly get some crossover distortion, especially at very low volume levels. If the bias creeps up too far and it turns these on too much, more than what's necessary, it won't affect the sound of the amplifier, but it will make them idle a lot warmer. So the transistors will get hot just sitting there. So the idea of the bias circuit is not only to just set this voltage here where it needs to be, but it's also to help it to track thermally so that it doesn't creep. Because semiconductors are very temperature sensitive. They're also current sensitive. So as you drive this thing at high volumes, when you're playing music through it, it will self-heat this transistor from conducting current. That self-heating will change the voltage drop on this gate or on this junction. But if it doesn't change here, but it's changing here, your bias is going to be off. That's how it works. So there's better ways to do that. The other thing is the rate at which this junction changes may not match very closely the rate at which a junction in the transistor changes. That's why you'll see special types of diodes called stabilizers in there in order to regulate that. They actually have a much different thermal signature than these do. Now, 1N4148, people will always say you can just replace stabilizers with a stack of these. If it's a 3-terminal or 3-junction one or something, just put 3 of these in. But really, these will not change with temperature in the same way that those stabilizers will. That's why they have them. That's why they use them. Now, there are other diodes that have a different thermal characteristic or thermal signature than these that you can use, like the 1N, 400s and 1N400s, I think. I'd have to look it up. There's a couple different ones that more closely mimic the thermal characteristics of a transistor junction. But just some interesting stuff to talk about there. Anyway, that's why you see these little square things attached to the heat sinks of your output transistors and of your or onto your driver transistors. Now that I think of it, when you look at the current project we're working on, the Spec 4, you can see where they mounted one of those. That's what this square thing is. That's one of the diodes in the bias circuit. It's attached right to the heat sink of the driver transistor. Now, these are a lot bigger, beefier transistors because this is a lot higher powered amplifier. But it's the same principle. So, long story short, this thing doesn't really have any bells and whistles on it. It is the base design of this type of amplifier. But what does it sound like? I mean, do you think it's going to have a lot of distortion, or do you think it's not going to have a lot of bass, or whatever? I don't know. Let's see. Okay, so let's turn the amp on. Turn the voltage up. That's the first thing I wanted to let you hear is let's turn this up, and what I'm going to do is I'm going to turn the power supply on, and you tell me if you can hear the thump. Did you hear that? And that's actually was the power supply coming up through that 5 volts from the last video. All right, so I have this connected up to my sound source, my input source, and I do have an external speaker protect box connected up. If there's any DC at all that gets on the terminals, this will cut the speakers, disconnect the speakers from the amp. So if something goes wrong here, because this is an unknown amp, at least the speakers will be protected. All right, let me start our Stranger Danger song, and let's listen to what it sounds like. Let me get the microphone here for you. Tell you what. So, yeah, this thing goes really loud for what it is, and I know you can't tell from on the other side of the YouTube world, but it's actually a very, very clear sound. And there's a lot of bass punch to this, and considering, just these little capacitors, it's all you need. Again, as long as you're not, you don't need excess of 10 or 15 watts, this is more than adequate. And there's your cheap Chinese parts. So we know that this works, and let me turn this power supply down to, well, let's do a couple things here. This will be the last part of this episode here. I'll connect this to the speaker terminals. And I'll turn this on to DC volts. And I'm going to put this microphone right next to the box. And when I get down to 5 volts, you're going to see this voltage go up. And when this goes up, you'll hear this click. So I'll just leave the mic right there. Do you hear it? Did you hear it kick out? It disconnected the speakers. And now it's in protect mode. And you can see I have quite a bit of DC offset. So we'll turn that back down. And then we'll have to wait for that to bleed off. And that's these capacitors here, because I have no voltage on the power supply. It's off. So that shows you how that works. But that's exactly how a speaker protect circuit works and what it's used for. So we know we have a working amplifier now. To my ears, which that's another whole story for a solder and chat one day, it sounds really good. I mean, it's something that I could mount this in a case, you know, and put some connectors and some jacks on it and stuff and hook up a set of speakers, and I could listen to this. It's not hard on the ears at all. So there you have it. No improvements, no nothing. Now, what we're going to do in the next video is we're going to use the oscilloscope, and I'm going to go through how to test certain things using a scope, because I know a lot of you have been asking about oscilloscopes. Like I said, I got a whole ton of questions from, you know, when I asked you what you wanted to see for these videos, and they were all kind of answers I got. And really, I think the most, which wasn't by a whole big margin, was questions about scopes. So we're going to, just like we did with the meter, we're going to use the scope and we're going to chase a signal through here. We'll disconnect the speakers, hook up a dummy load, and we'll just do some tests with that. That'll be the next video after this, you know, in this series. So, as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon with another fun episode. I'm actually enjoying this. I mean, I'm learning a lot of things too, just, you know, tracing through all this. So, until next time, stay well, everybody. Bye-bye.